Okay, but this week, Lagrangian mechanics, part 3. Woo! Now, this week, we are going to be doing some fun stuff with, well, we'll just do a lot of different coordinates. But let's talk more about last time. Last week on Physics O Lagrangian Mechanics, we talked about the multivariable calculus of variations. Again, this calculus of variations being this this calculus of changing functions inside of integrals and how much they change by small variations. So we had to, figure that out. And of course, in some situations, we want that to be a stationary point or be like a minimal change or a zero change. So we did all that the first week, and then again, we finished that next week. Again, we are following along with the book Taylor, John R. Taylor, great classical mechanics book.
Last week on Eric had an episode.
Last week on Eric had an episode. So we're following along with John Taylor, as well as I put all my notes on Discord, !Discord, and you can find the notes for every week in the discussion series notes section. So again, last week we did multivariable calculus of variations, and we still found that that if we just had some graph, right, and we had some point on the graph, we'll call it A, and another point on the graph B, and we want to consider every single path from A to B, and it doesn't matter what it is. We can figure out with two dependent variables, it didn't really matter. It always turned out that the shortest distance between those 2 points shortest distance was a straight line. And that was given by y equals mx plus b. Now, we also talked about the Lagrangian. We introduced the Lagrangian, and we gave it its form of kinetic minus potential. And we found that if we let this be the form of the Lagrangian with kinetic energy and potential energy, then the Euler and Lagrange equations were a natural occurrence in Newton's second law, i.e. F equals the change in potential with respect to time. Force equals ma, right? Everybody knows it, loves it. Force equals ma. Newton's second law, we found out that the Euler-Lagrange equations came naturally from F equals ma, and then those Euler-Lagrange equations belonged to an action, which was minimizing the time of the Lagrangian. And we're gonna reference this, but we're not gonna solve it. Like Taylor solves it, but we're gonna skip that. We're just gonna reference it. And yeah. So remember this. We're gonna bring this back later. Let's see. So then there's a couple things we can say about this, right? That we didn't quite get to last week that we'll talk about now. That this teaches us that for a particle, the following three statements are equivalent. A particle's path is determined by Newton's second law, F equals ma, right? That can tell you exactly how a particle is moving. If you take introductory physics, you take introductory physics 1, you'll talk about Newtonian dynamics for the first half of it, at least, if not more, right? Before you even get into like inertia, before you even get into like thermodynamics and everything like that, you can talk about the trajectory of a particle just using Newton's second law. Secondly, you can talk about a particle's path determined by the Euler-Lagrange equations, right? Again, we saw that those come out of this. So if you can do everything with Newton's second law, you can do everything with the Euler-Lagrange equations. And lastly, that same path therefore meant that that's a minimization of the action. We call it the Hamilton's principle. Minimizing the action will tell you the trajectory, or the path, I should say, of a particle. So a particle's path is determined by a stationary point of the action. Now, I also said last week that one of the bonuses of Lagrange mechanics is that you can use it in any coordinate system, which is kind of fancy, kind of nice. So that's the majority of what today is going to be, is kind of looking what the Lagrange equations look like or the Euler-Lagrange equations in any given coordinate system. So let's use a generic coordinate system. R is equal to, we're going to just call it Q1, Q2, and Q3. And they can be in Cartesian, cylindrical, spherical, whatever you want to do. So now let's talk about the Lagrangian for these coordinates. The Lagrangian, of course, is going to be, some t minus u. So that might look like 1/2 m r dot squared minus the potential with respect to this r. This you could write as some Lagrangian of all of these, which might have the following. Remember, our Lagrangian usually consists of the coordinates themselves and then their derivatives with respect to time. When we need the action, this is the Lagrangian we want. And we see that they show up, of course, in the r's, because we could write our r's in terms of these variables. Right? I mean, like, we're going to do it, right? The action is the integral from t1 to t2 of this Lagrangian. Now, what does that mean? Well, since our action is unchanged, any stationary points are still found by the Euler-Lagrange equations. That's one of the things we found last time, is in the multivariable calculus of variations. It didn't matter if you had multiple variables, they all go down to the same Euler-Lagrange equations, right? So we can write down a more general form. The derivative of the Lagrangian with respect to some coordinate, we'll call it qi, is equal to the derivative with respect to time of the derivative of the Lagrangian with respect to q dot I, for some I equal to 1, 2, or 3, right? And you can, like I said, so then you can split them up. You can have a generalization of this. Each of these holds true for each individual version of Q, regardless of what the Q is. If we're in cylindrical or Cartesian or spherical, it's all good. It's all gravy. So there's one thing we should say. There's a big note that Taylor warns us about, and that is that this is true for any coordinate. Now, some coordinates might exist in a non-inertial reference frame of reference, right? If you are sitting on a tilt-a-whirl and you're spinning around, you experience some centripetal acceleration. Therefore, you are not in an inertial reference frame, right? Because you have experienced some rotational velocity, and some radial acceleration. But if you're, just traveling linearly, then you are an inertial reference frame. So here's the issue. This works for any coordinate system, inertial or non-inertial. But the Lagrangian, let's go back to chat so I can see what you lovely people are saying. Okay, now, where are we at? All right, so we do need to make sure that the Lagrangian is in an inertial reference frame. The Lagrangian needs to be an inertial reference frame. If we take care of that step, then the coordinates, this is true, regardless of the coordinate system, inertial or none. Steven, AQ20, welcome to the channel. Thank you for the follow. Okay, so when talking about Newton's second law, this generalized equation looks like the following. So when we did this last time, we saw that this had some sort of generalized force. We figured out that F, you know, in some direction is equal to the change of the momentum in that direction with respect to time. Ryman, welcome to the channel. Hopefully I got that right. Thank you for the follow. So we found out that that was true, and because of that, we can make some generalizations about this. When we set this Lagrangian to be what it was, we did this, did the Euler-Lagrange equations, backtracked to the action. That was all last week, so we're not going to redo it again. But we did find that this turned out to be, where should I write this? Let's erase this really quickly. This turned into some generalized force.
Come here, Darla. The people need
I didn't
you.
know if you guys could hear her or not. She's been, lately she's been attacking right outside the door for some reason. I don't know why. Well, I do know why. It's because I have an underground conduit that runs my internet out here, and she found it. And now she wants the entire conduit to herself. That's a big stick for her to pull. Okay. So if this was generalized force, we found that this is
She
generalized.
is drawn to us. Of course we can sense her.
I just spelled that terribly wrong. Generalized change of momentum. So this is what we figured out. We figured out that this side of the Euler-Lagrange equation, generalized force. This side, generalized change of momentum. That's going to come in handy quite a lot when we start changing into different coordinate systems. Hey, speaking of that, let's change to a different coordinate system, huh? What do you say? Let's consider something spherical. We'll work in polar coordinates, huh? Let's do an example of an unconstrained particle in 2 dimensions in polar coordinates. Now, if you guys have taken classical mechanics, you know that the force equations, if you wanted to write down Newton's second law, it's not straightforward. It's not just MA. Well, it is MA, but the A is radial, and it has some weird components to it. It's not just some change in R over change in T. You have this extra term that has the change in the angle as well. So to go from, you know, Newton's law in Cartesian coordinates to polar coordinates, we had to add some terms that weren't necessarily intuitive, right? Let's see what happens when we do it with Lagrangian mechanics, okay? So example, let's find the Euler-Lagrange equations of a particle moving in 2D, or wait, in a constant force. We'll call it a force field, but you get the picture. Just there's some force that's a gravitational, electric, whatever, it doesn't matter. Some sort of force is moving it. In 2D polar coordinates. Cores. Is this related to the ramps and balls you built some time ago? Yeah, it's similar. It's gonna be, we're gonna be finding the same concept. It's minimizing the action. So in that sense, yes, it's the same thing, except now we're doing a different form. It's just something moving in 2 dimensions, but now we're trying to see it has circular motion. So we want to have some sort of polar coordinates. But yeah, it's the exact same concept of minimizing that action. The Euler-Lagrange equations are the thing that minimizes the action. So the first step is to write down the Lagrangian, right? Lagrangian can be written with all these things. You'll have R and phi, and then R dot and phi dot, which is equal to, of course, RT minus U, where T is kinetic and U is potential. But now we want to talk more about what the T is. We have our 1/2 mv squared, right? We want to use 1/2 mv squared for this. But we need to know what V is. And it gets a little complicated, right? Because we have two directions. Remember before, if we had two directions like X and Y, we just had we just had 1/2 mx dot squared or 1/2 my dot squared, and we just added the two together. Now, it's gonna look a little different because what's the velocity for a radial velocity? Well, radial velocity is just gonna be r dot. Excuse me. The radius as it changed with respect to time. However, what's the angular velocity? Angular velocity is different. Well, I should say this is an angular velocity. This is the velocity. This is actually technically the tangential velocity. If you remember the tangential velocity, it's r phi dot. Cosmolano, welcome to the channel. Thank you for the follow. If the velocity is angular, or I should say tangential, then we can say it's equal to r, and this would be the angular velocity, right? Phi dot. It's how phi is changing with time. So if you make this motion, right, and you call this some small phi, then it's changing with time as I draw this circle. This is moving all over the circle, and we could go around, round, and round, and round.
Welcome to the channel. Things get a little bit weird.
Soul Bevin 79, thank you for the follow. Welcome, welcome, welcome. Hope you guys like Lagrange mechanics. Now, so if we want to do this, we have to include both of those. So our real Lagrangian is going to look something like this. 1/2 m r dot squared plus r squared phi dot squared. I might ask you guys a question. Do you guys want to answer a question? I know sometimes you guys are all like, you know, just push the box up the inclined plane, man. We're here for a good time. We don't want to answer questions. But I'm going to ask you a question. Why bother with changing this velocity to the tangential one as opposed to having r phi dot? The Lagrangian needs to be inertial. So why? I'm going to ask you this question. Why would we have v phi equal to r phi dot? I'll put it in relative coordinate space. We'll take it. We'll take it. You want inertial frame, right? You want an inertial frame. So you need tangential velocities because it's linear, as opposed to angular velocity, which would not be a tangential, which would not be an inertial reference frame. Remember, I said the Lagrangian needs to be built in the inertial reference frame. Inertial frame, yep. Bingo. Excellent, excellent, excellent. So now that we have it with our radial velocity, which again is radial velocity, it's just like, listen, if this is your thing and this is your circle, this is pew, it's radial velocity. It's changing with respect to time. One Dark Vision, welcome to the channel. Thank you for the follow. Okay, now, what does that mean? Okay, so if we have the Lagrangian in our inertial reference frame, then that means that, oh, I should erase this too. This is gonna cause confusion. Okay, so now that our Lagrangian is complete, it's in our inertial reference frame, now we can use our Euler Lagrange equations. Those are good for any coordinate, so long as the Lagrangian is in the inertial reference frame. Whew. Let's write it down. The partial derivative of the Lagrangian with respect to the radius, we'll do the radial one first, is equal to the change with respect to time of the derivative of the Lagrangian with respect to r dot. Now, if we plug this in and we take the respective derivatives of the Lagrangian as one would want to, then the left-hand side of the equation becomes m r phi dot squared minus the derivative of u with respect to r, which is equal to, I think she found her ball, so I think she's happy now. The change with respect to time of m r dot, or m r double dot. Now, as we talked about before, just finished my meeting for the day. How's everyone? I'm good, sir. How are you? Good to see you. So as we talked about before, if we want the force, we could talk about the radial force as being the change of u with respect, the negative change of u with respect to the change in r. That's nice. We've seen that before, but that's going to take a different shape in just a second because it's going to lead us astray in a moment here, as I'm sure some of you have already come to realize. Now, if this is the force, that means we can say that the radial force is going to be equal to this term right here. So we're going to pull this to the other side, and we'll find that m times r double dot minus r phi dot squared. This is the Newton's second law in polar coordinates, right? This right here. So again, we re-derived Newton's second law in polar coordinates, but this time we didn't need to remember that the acceleration was different. We didn't need to remember that the acceleration of the radial had this extra term. This extra term, does anyone know what this is called, where it comes from? Keeping phi for shame. So that we need the phi because it has a name. And this is, what is the name of that term? And yeah, so then we have this extra term. It's not just a change with radial. You might think, well, if it's just going to be the radial acceleration, then it's just going to be, you know, r double dot. You know, you take the time derivative one more time. But it's not true. You actually get something else in Newton's second law that is that has a name. I did the cardinal sin by asking a second question. Something that starts with a C, you know, because you read today. It's centripetal. You are both correct. Centripetal acceleration. Okay, now let's. So we have to do phi now, right? So it's nice. All we had to do is plug in our normal Lagrange equation, and we naturally got all of the pieces that we need without having to do anything that was unusual. So now, can I do the tangential ones over here? How much room do I need for these? I might need more room for these. Let's erase the radial one. I want to leave up the Lagrangian though. So maybe we should take a second right now. Let's just do it really quick. Okay, so we get the Lagrange equations. Let's put them right here. And they are going to be for phi now, because we did the r direction. Now let's do the phi direction. Or I should say the phi variable. So this is another stationary point. Oops. Phi dot. Okay, so there's our Lagrange equation, and all we did again was a lot of brick veins in the chat. I'm drunk already. There it is. Insert some candy. Oh man. Anyways, so yeah, so now we have phi dot here, and yeah, so now we have the phi equation. So let's do that one really quickly. So if we apply this to here, we end up with negative the derivative of the potential with respect to phi, and then this change with respect to dt of m r squared phi dot. Okay. But we have kind of a party foul here, right? Does anyone know what the party foul is? Well, it has to do with this term, right? Because this is not true. Or, well, this is true. It's not equal. What's true is that the force is not equal to this, right? Why? Because what's the actual force? The actual equation, excuse me. The actual equation is equal to the gradient, the negative gradient of the potential. Tyrion spilled his drink. Probably. So the negative gradient of the potential means that when you're in polar coordinates, you actually get something that looks a little different. It's 1 over r. I think it's minus still, right? Is it minus still? Yeah. I think it's minus still. I actually don't remember what the book said. I think I added this part. So yeah, so we can do that, or we can say that R times F is equal to negative the derivative of the potential with respect to phi. Okay? Gradient and polar coordinates. I smell momentum. This is a funky trick. So now, how does this turn into? Well, how does this turn into? Well, on the left-hand side, we have R times F. Does anyone know what this is? R times F, a distance times F. And on this side, we have d dt times m r squared phi dot So you have two questions right now. What's this? And if you're looking at the notes, you'll know. And what's this? Distance times the force, Pog. Torque! You said party foul, so I naturally thought of alcohol abuse, spilling it. Oh, I see. That would be a good thing to think about when I said party foul. I imagine Tyrion is, I imagine Tyrion is happy. Anyways, I don't know where I was going with that. This is a funky one. This is the angular momentum, right? Angular momentum, you might see something that looks like this. Maybe we'll hold off on that for a second until we get to the end. I'll show you the whole form of it in a second. But notice here how this is torque and this is rate of change of angular momentum. Okay, well, what does this all mean? Well, remember how we said that this would always be some sort of generalized force? And this would be some generalized momentum. Well, what happens here is we have circular motion, and that's why sometimes, this is why sometimes it's, anyways, this is why sometimes it's convenient to say that torque is like a circular force. Right? Because this is what we found in the Euler-Lagrange equations. I know it's not like the most correct thing, but this is what sometimes we might say to like an introductory physics class or something. Someone trying to understand what torque is. Torque, I don't like Lagrange. I'm sorry, Crafter. But torque is kind of like a circular force. This is generalized force in the phi direction. So in circular motion, we have a circular force, a generalized circular force. And in here, we're going to have generalized momentum. Still, again, circular force. Therefore, it's angular momentum, right? And we'll see the full form of that in just a second. Okay. So this makes sense, right? This is still our thing. Here's generalized force. Here's generalized momentum. Hooray! All right. So again, this is a really nice rule, or this is a really nice result because it follows the basic rule that if there's a generalized force, then this is a nice rule because now if we set the torque equal to 0, what is going to happen? So if there's no torque, right, then what's going to happen to the generalized momentum? Well, if you take the if you take any derivative of a number and it's equal to 0, then this is going to be equal to a constant, which means that the linear momentum is conserved, which is good, which is nice, because this is kind of like a general basic rule of thumb, right? That if you do not apply a force, then you get a conservation of momentum. That momentum is not going to change. That should be true linearly. That should be true angularity. And it is. We can figure this out. If you set this equal to 0, then this term right here, this generalized momentum, is a constant, and it's not changing. I smell conservation. Yes. So we're actually going to do the conservation laws at a different time, but we can use this to sort of derive and kind of look at some conservation laws by using this Euler-Lagrange equations. There's so much physics happening in just a small little equation, from like generalized force, whether it's linear or angular, to generalized momentum, whether it's linear or angular. And then also if the force is 0, then you expect that the momentum is going to have some constant value. It's going to be conserved. Yeah, so we'll talk about that a little bit later. Taylor does it in 7.8, and today we're only going to be at 7.2 or 3. But yes. Clunky, welcome to the channel. Thank you for the follow. Like your name. Okay, so let's erase this and head into the next part. So that was a fun, I mean, that's a huge and fun example showing you the power of the Lagrangian, the Euler-Lagrange equations, and how and how you don't need to worry about the coordinate system as long as that Lagrange is in an inertial reference frame. Then the Euler-Lagrange equations hold true as a stationary point of the action. I can't remember the name of the first human I kissed. Okay, what? But I remember when angular momentum kissed me. Okay. Torque times RPM equals pony power. The radius of the electron might be 10 to the negative 81 meters. Tiny, but not 0. Stephen Wolfram. Interesting. Could we have anticipated that conservation? I wonder, probably. We talked a little bit about it, but we'll probably not talk about it more. I think what he's getting at is if you have, I think Zert knows the answer to this. I think he's leading me into it. That if you minimize the action, then you won't have any extra energy, so it should be a 0. But let's talk several constrained particles. It's not gonna be like, this is more of like, we're gonna need this later, so we have to talk about it. But there's nothing gonna be like super unusual here. You can almost imagine exactly what's gonna happen with several constrained particles, right? So now we're talking about unconstrained particles. Why do I have constrained there? Excuse me. These are unconstrained particles. Checkmate Wolfram. So these are several unconstrained particles. Constrained particles are next. We don't want to constrain ourselves yet. So several unconstrained particles. And then basically the ideas from everything we've done up till now are going to remain the same. It's just going to extend them to many particles. So let's just consider 2 for now. Consider 2 particles. Okay? And unconstrained, moving around freely. Our Lagrangian, R1, R2, and then the dots, the time derivatives of those. And then, of course, we're going to want some Lagrangians. So we're going to want kinetic minus potential. So we can imagine that this is then going to be equal to 1/2 m1 times r1 dot squared plus 1/2 m2 r2 vector dot squared plus, here we go, minus the potential, whatever they are, of r1 and r2. So the forces follow as usual. We'll have the force of 1 is equal to the gradient of the potential for the first coordinate system. The same thing for the second particle. 2 and applied to u. And then it follows that we're going to get a bunch of these things, right? We'll get the force equations, or Newton's second law, I should say, in every single p dot, p1x, f of 1y equals p1y dot, I should say p dot 1y, And then that will carry on all the way to f of 2. The second particle, the z direction, is equal to p dot of 2z. So again, we're going to get like what we expect to get, right? All electrons are just virtual particles. Ugh. And we can get our 6. So we'll get 6 Euler-Lagrange equations, right? Again, you can just imagine what they look like. I'm not going to write them all out. There's several written in the book, in the notes. I'm probably not even going to write those. Equals the change with respect to time of the derivative of the Lagrangian of x dot with respect to x dot. And you get the picture. We can just write 1 for every single one for y1 and y dot 1. And then for z1, z dot 1. And you know the same thing, x2, y2, and z2. Now, this generalizes. Of course it would generalize. It generalizes nicely, right? And that's just for an n-particle system. We'll get our normal Lagrange equation for each and every single coordinate. d dt, the derivative of the Lagrangian with respect to q dot I. So we're just going to pick some random coordinate, q dot I, and then for some n particles, so for n particles, I is going to equal 1, 2, dot, 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 all the way up till 3n, right? Because we're going to need 3 times the amount of particles, because each particle will have an x, y, and z coordinate. Okay, now, so that's for unconstrained particles. I wrote constrained again. Why do I keep writing constrained? It's not supposed to be constrained, no. So if you're in the notes, the 2 times I wrote constrained, it needs to be unconstrained. Okay, we got one more thing to do. And that's 7.2. See what I did there? Let's so let's do a constrained system. Now that we've done all of the unconstrained stuff. And how will our constrained system look like? Well, let's consider a pendulum. So we're going to have some wire here with a, as Taylor calls it, a bob. And this is going to have length L. It's going to be some phi. We can talk about the y coordinates and the x coordinates. Okay? So we're going to have some bob on a string. And let's just say we've talked about it before. Another huge perk is, like, so we talked about the first perk, which was that Lagrangian mechanics can happen in any coordinate system. And the Euler-Lagrange equation is fine, whether it's inertial or non-inertial. It's just as long as the Lagrangian is inertial. Now, another cool perk is that we can work in constrained systems, like a pendulum. How is it constrained, you may ask? Well, let me tell you. The bob, the bob can move in the xy plane. However, it's constrained by, we'll just call it Bob. Bob is constrained by the following. X squared plus y squared is equal to L, right? That has to be true. Has to be, if it was going to be like a woo, 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 it'd make a unit circle with some radius L, right? So this has to be, it's the constraining point, right? So as we did last chapter, let's pick one coordinate to be independent. So you could do this, there's 2 ways to do it basically. You could pick this one coordinate to be independent, L2, L squared minus x squared. That is fine. That means that y depends on x. X is an independent variable. As we change x, y will change naturally. However, we might find more success. So this works. But let's do phi. Because why not? Right? We're bold. We're ambitious. I need to make my notes tonight from Taylor. I feel constrained. I need more fiber. Dude. So what would our kinetic energy be if we used our phi? Well, we can figure it out. It's going to be 1/2 mv squared. We know that there's no radial direction. So it's just going to be the v squared or radial velocity, right? It's not changing in radius because we're not like lifting it up and dropping it. We're just letting it follow that path along the unit circle that it makes, right? Or the circle. I need to stop calling it unit circle. The circle that it makes, right? And so this is going to be equal to 1/2 ml squared phi dot squared. Now, the potential energy is therefore going to be mgh. We know that to be true. So there's one other question.
The people need you.
Unit circle says what? So the other question we need to ask is, what is h? Right? Well, we can figure out h. If we take this to be like, h can be here, and then we can make a triangle, right? This side of the triangle is L minus h. This side of the triangle is L. This side is who cares? We don't need it because cosine of phi is equal to adjacent over hypotenuse. So L minus h divided by L. Sorry for the barking dog, everybody. She'll probably quiet down in just a minute. Okay, so then we can solve for h, and h is going to equal L times 1 minus cosine phi. Okay? Which makes sense because the higher the phi then, or the larger the phi, the larger the h. So it makes sense. Good. Excellente. Now, that means we can solve we can write down our Lagrangian. Okay? So our Lagrangian is therefore going to be 1/2 ml squared phi dot squared minus mgl 1 minus cosine phi. Now, in a single coordinate, this is all we have. We have a single coordinate Lagrangian. The single coordinate being phi. Well, phi and phi dot, right? So the Lagrangian will be written as some q and q dot, right? So now that's all we have. We have q and q dot. That's it. Phi and phi dot. So now our Euler-Lagrange equation. Let's write that down. This is our best friend for solving all of these things. We don't need to worry about what coordinate it is. We don't need to worry about whether it's circular or linear or whatever. This Lagrange equation will take care of everything for us. Oh, I should probably just write phi instead of q. I mean, it seems like an unnecessary step. So phi and then phi dot. And what does this look like? Well, let's write it down. On the left-hand side, we have minus mgl sine of phi. And on the right-hand side, we have the derivative with respect to time of ml squared phi dot. What are these two things? Well, let's write down them as cross products. Okay? We're going to work our way backwards a little bit and take a look. And here, if we were to write it down as a cross product, we'd have the length vector cross the force due to gravity. What's that? On this side, we could write it down as an angular momentum. That's fine. This is a change of angular momentum. Or we could write it down like this. ml squared phi dot, double dot, where ml squared has a particular role. If Dodo were here, he would say, I smell momentum again. I'm actually gonna change it up a little bit. If Dodo were here, he would say that's moment of inertia of a particle, right? And this is the angular acceleration. So what's that equal to? Well, this is then going to tell us that the torque, oh, he does gamma, capital gamma, so we'll do that. That the torque is equal to the angular, or I'm sorry, the moment of inertia times the angular acceleration. Which is one of these things that we've learned about time and time again in classical mechanics, but now we kind of see it come to fruition, right? The torque that you apply to this, the gravitational torque, is equal to the moment of inertia times the angular acceleration. What a fun result that we get from simply just applying the angular acceleration, or I'm sorry, from simply just applying the Lagrange equation to the phi equations as well. And of course you could get a result in x and y's, that'd be fine, but it wouldn't be so pretty and we wouldn't get the moment of inertia and everything. You probably could, of course you could in some sense, but this one is very nice. How cool is that? Wow, why am I so dark now? Let's see here. I don't really want to change the exposure. So I'll just have to lean forward and get into the light. I hate you less. So what do you guys think? Other than Tyrion. We know he likes it and he hates me less. But for everybody else who hopefully didn't hate me when I started 50 minutes ago, I'm presuming you still don't hate me. Hopefully not. This is cool. I really like this. I like all of the results. Like every week I get to be like, this cool thing is happening. And that's exciting. And it's because like I haven't learned this, I think, since I took the class. Because Milano, this is your way of teaching a class and I just randomly showed up here? Nope, I don't teach a class on here. This is all just for you guys, for the viewers. So it's however you guys want. Ooh, what's that? Is that a bee? I think it's a fly. I think it's a fly. Okay, whew. So this is completely viewer oriented. I answer questions. I am a particle PhD student and I just answer questions and teach physics to anybody who wants to learn.